Welcome to the deep dive.
Mm.
Today, we are taking on a document that is, the bedrock of any modern building, the National Electrical Code. And for anyone who works with or even near electricity, the NEC, officially NFPA 70 2023 edition. That's basically the law of the land for safety.
And you might think, diving into something this massive is just overwhelming. But our goal today is to give you the ultimate structural shortcut.
A shortcut. How about
It
that?
is. The NEC looks like a wall of technical rules. But if you understand how it's organized, that's the key to being, well, instantly informed. Our sources really focus on that organizational map.
Specifically the cross-reference tables.
Exactly. Those tables connect the basic rules to all the specialized dangers.
Right. So this is a deep dive into structure. We're going to unpack the NEC's backbone, which is Chapter 2, Wiring and Protection.
Foundation.
And then we're going to use the code's own internal logic, its cross-references, to show how those foundational rules connect out to, specialized installations. Everything from marine environments to solar arrays.
Our mission today is to show you not just what the rules are, but really where to find the exceptions and the modifications that keep people safe.
Okay, let's start with the big picture then. The NEC is broken down into 9 chapters. It moves from the general to the really, really specific.
It's a very logical progression. You start with Chapter 1, which covers the general rules, definitions, that sort of thing.
Right, the admin stuff.
And then you immediately hit Chapter 2, Wiring and Protection, which is our focus today. Then it goes to Chapter 3, Wiring Methods and Materials, and Chapter 4, which is Equipment for General Use.
And then as things get more complex, the chapter number goes up. So Chapter 5 is for special occupancies, Chapter 6 for special equipment.
Chapter 7, Special Conditions, and Chapter 8 is all about communication systems.
9 is just tables, right?
Chapter 9 is just the essential tables, data points, calculations. But you've hit on the critical point. Chapter 2, Wiring and Protection, has to be understood first.
It's the core.
It is the core. It contains the universal laws of electrical safety, the physics and design principles that have to apply before you even consider any exceptions. It's the kernel of the operating system, really.
I like that analogy. So let's break down what's in that kernel. When we talk about core concepts in Chapter 2, we're really talking about the flow of power.
Exactly.
So we have services, feeders, and branch circuits.
Right. And you can think of the electrical system in a building like the human circulatory system. The power comes in through the services. That's Article 230.
That's the main artery from the utility.
Precisely. And from there, it moves through the large feeders, Article 215, which are like the major veins distributing power to different areas.
And the final delivery. The little capillaries.
That's your branch circuits, Article 210, the ones feeding the individual outlets and lights. Perfect analogy.
Okay, so if those are the pathways, what about the system's defense? How does it protect itself?
That's the crucial protection piece. And Chapter 2 handles the 2 most important defense mechanisms. First, we have overcurrent protection.
Article 240.
Article 240, this is the system's main defense. It's your fuse or your breaker, and it makes sure that when a fault happens, the power just stops before the heat can cause a fire. It's the ultimate safety brake.
And the second defense, which I think can be a bit confusing for people, is grounding and bonding. Article 250. Why is that considered protection separate from the overcurrent device?
Because overcurrent protection handles overloads, but grounding and bonding, that manages fault currents. I mean, the sudden, dangerous return path to Earth.
So it gives the electricity a safe place to go.
A low resistance path, yeah. It ensures that if a hot wire touches something metal it shouldn't, the current has an easy way back to the source. And that is what allows the overcurrent protection, the breaker, to trip immediately.
So they work together.
They have to. And those 5 articles, 230, 215, 210, 240, and 250, are the absolute non-negotiables for any electrical system. I don't care if it's a shed or a skyscraper.
Okay, so we've got this foundation in Chapter 2. But obviously, the rules for wiring a standard office aren't going to be enough for, say, a hazardous chemical plant.
Not a chance.
Our sources point to Section 225.3, other articles, which has a table. Table 225.3.
This table is the secret sauce. It's truly the shortcut to being a code expert because it answers that crucial what-if question.
What if I put this power system somewhere unusual?
Exactly. What if I put it in a unique place? If you are applying the general rules from Chapter 2 in, say, a wet location, this table forces you to stop and go look at the specialized rules.
So it's a structural mechanism to prevent you from missing something.
That's a perfect way to put it. It prevents a designer from accidentally missing a critical safety requirement. It establishes a hierarchy.
And the specialized rules always win. They override or add to the general rules.
They have to. And the table shows you that relationship by cross-referencing certain general articles that apply, everywhere. For example, conductors for general wiring, Article 310, is referenced constantly.
Okay, and Article 310 is what dictates wire size, insulation type, ampacity.
All of it.
So no matter what, I have to follow the sizing rules in 310. Why is that specific reference so constant?
Because the wire itself is the common denominator, if you use the wrong size wire, if it's too small for the current, it's going to overheat and fail.
Doesn't matter where it is.
Doesn't matter if you're in a dry office or an explosive atmosphere. Article 310 is about the physical limitation of the material. Same with Article 200, use and identification of grounded conductors.
The neutral wire.
The white neutral wire. It has to be a neutral, always. You can't use it as a hot wire. That's a foundational safety rule that holds true no matter what. These are the constants.
Okay, here's where it really gets interesting, I think. Once you start looking at the specific articles in that table, you realize the NEC is built for every conceivable hazard.
Oh, this is the fun part. The insight here is that the safety standard has to adapt based on the conductivity of the environment or, how permanent it is.
Take water.
Water is the perfect example. The second electricity gets near water, the standard grounding rules from Chapter 2 are, well, they're beefed up dramatically. We see specific articles for marinas and boatyards, Article 555.
And of course, swimming pools, fountains,
Yeah.
Article 680. That one's famous for being strict.
Extremely strict. And in a pool installation, the standard grounding from 250 just isn't enough.
So what changes? What makes it different?
You move from simple grounding to really aggressive bonding. You have to bond all the metal components together, the ladders, the railings, the pump motors.
Why?
Because water is conductive. Even a tiny voltage difference in the water could be lethal. The general rules don't mandate that level of metallic continuity, but the specific water-related articles do.
And it's not just pools. I see even fixed outdoor electric de-icing equipment has its own Article 426.
Right, because of the constant exposure to moisture and physical stress, the code has to account for that.
We also see modifications for structures that, that move or generate their own power.
Yes. Think about transient housing. Mobile homes, manufactured homes, all covered under Article 550. They have specific rules for their feeders and wiring.
Because they get moved around.
Exactly. There's a different kind of mechanical stress than you'd find in a fixed building.
And then there's solar photovoltaic systems, Article 690. This is a great example of where Chapter 2 rules, which assume you can just kill the power at the main disconnect, are completely inadequate.
Absolutely inadequate. A solar system, even when you disconnect it from the utility grid, can still be generating current if the sun is out.
So it's always lived somewhere.
It can be. And that continuous generation is the safety puzzle the code has to solve. Article 690 demands very specific disconnect requirements and signage, so first responders know how to safely de-energize both the AC side and the DC source circuits. It completely overrides Chapter 2's typical definition of a disconnect.
I think the most extreme example of this override logic has to be hazardous locations, Article 500.
Without a doubt. In a location with, say, flammable gases or dust, the normal Chapter 2 wiring methods are just thrown out the window.
So what do you do instead?
You have to use explosion-proof enclosures, special sealing methods. The priority shifts from just protecting against shock to preventing any spark, no matter how small, from causing a catastrophic explosion.
So the hierarchy is clear. The specific hazard comes first, general rules second.
Always.
Okay, so we've seen how the environment changes the rules. Now let's look at how the rules change when we dial the power magnitude way down to signaling levels and then all the way up to utility levels.
It's a great contrast. It shows the full spectrum. It's so important to recognize that the NEC manages more than just power distribution. It manages energy limits. Meaning we separate low power control and communications wiring from standard power wiring, because the danger isn't necessarily a massive shock, but the uncontrolled flow of energy that can start a fire or disable a life safety system.
Right, so why do they need different wiring methods? Why the separation?
Well, you have articles like Class 2 and Class 3, remote control and signaling circuits, which is Article 725. Those systems are designed to inherently limit the energy available.
They're power limited by design.
Exactly. And they need separation from the general branch circuits to prevent a short from injecting dangerous amounts of energy into equipment that just isn't rated for it. And even more critically, fire alarm systems Article 760 have their own strict rules because their reliability has to be guaranteed.
You can't have a fault on a regular lighting circuit take out your fire alarm.
You absolutely cannot. That life safety system must survive.
Which makes this shift to high voltage even more profound. We go from circuits with tiny amounts of energy to circuits with massive energy levels, where the danger is just exponential.
It's a completely different world. When you cross that threshold of 1,000 volts AC or 1,500 volts DC, the general rules of chapters 2 and 3 are fundamentally inadequate. The properties of electricity literally change at that level.
So you need totally new rules.
You need specialized rules, documented in articles like over 1,000 volts general, which is Article 495.
What's the biggest thing that changes when you cross that 1,000 volt line?
Everything. Your standard overcurrent protection from Article 240 is replaced by specialized protection from Article 245, designed to handle massive surge energy. The insulation required is totally different.
So you can't just use standard wire.
No way. You move from the general rules in Article 310, conductors for general wiring, to Article 311, medium voltage conductors and cable. The general rules just don't account for the air clearance distances you need or the insulation thickness required to contain thousands of volts.
And I see it even addresses older methods like open wiring on insulators, Article 398.
Yeah, which shows the code's historical depth. You don't see that much in modern low voltage work, but for high voltage oversight, it's still there. It's still critical.
So after all this, what does it all mean for you? We started with the backbone. Chapter 2, services, feeders, circuits, overcurrent grounding.
The fundamentals.
And we saw that the NEC is this unified, really intelligent system where Chapter 2 acts as a central hub, constantly pointing out to highly specialized rules.
Whether that's because of water in a marina, or the generating capability of solar panels, or just the sheer magnitude of high voltage.
The real takeaway here seems to be that you can't achieve electrical safety by just reading Chapter 2 by itself.
You can't. It requires recognizing that the hierarchy of safety is determined by the hazard. If the environment changes or the voltage level changes, the fundamental rules of protection have to be updated. That critical cross-referencing is what ensures safety across the entire spectrum.
As we've seen, the code makes a sharp distinction between the rules for conductors for general wiring in Article 310 and medium voltage conductors and cable in Article 311.
And here's the final thought for you. Consider this. Why is the change in required insulation, spacing, and protection so dramatic that the entire definition of the conductor has to move from a general article to a medium voltage one?
It's because the risk is completely different.
It's because once you hit, say, 5,000 volts, what was a safe clearance at 120 volts becomes completely lethal and insufficient. The magnitude of power fundamentally changes the physics of danger, and that forces the code to abandon its general framework and create a whole new set of rules from the ground up. That transition point is the ultimate measure of electrical risk.